Hello everyone, and welcome to our presentation on analysis of sorting algorithm. My name is Miguel Calumba,
My name is Alexis Aris Tribucas.
And my name is Carlo Palon.
and today we'll be walking through to our system which presents how several sorting algorithm works. Let's get started. Sorting algorithms are essential in computer science for organizing data efficiently, whether it's for improving search performance or for preparing data for visual representation. Sorting plays a crucial role in many applications. In this report, we analyze and compare several popular sorting algorithms in terms of their working principles, time complexities, and stability. So the first one is bubble sort. Bubble sort is a simple sorting technique. Imagine it as a sorting method where the largest or smallest items bubble up to the correct position through repeated comparisons. Let's picture our datasets as a list of students' record displayed in a table view. Each student has various fields like their ID, name, year level, and score. When the sorting is triggered, say by score, the bubble sort algorithm goes through each pair of adjacent students one by one, comparing their scores. If two adjacent students are found to be out of order, meaning the first student's score is higher than the second student's when sorting in ascending order, the algorithm swaps their position. The process repeats until all records are in their correct position. Specifically, bubble sort uses two loops, an outer loop that ensures each item gets sorted into its correct place, and an inner loop that makes the actual comparisons and swaps. After each complete pass through the list, the largest or the smallest, depending on the sorting order, item settles at its final sorted position at the end of the list. Each subsequent pass requires fewer comparisons because previously sorted elements are no longer checked. Now, let's examine two scenarios, the best case and the worst case. In the best case scenario, bubble sort performs the least amount of work. This scenario occurs when the data is already sorted. Even though our implementation in JavaFX still execute every pass, it won't perform any swaps, as all adjacent pairs are already in order. Technically, an optimized version of Bubblesort would detect this and stop early, but our current code doesn't have this optimization and thus continue through all passes performing n-1 comparison for a list of size n. Conversely, the worst case scenario arises when the data is sorted exactly in the opposite order of what we want. In such situation, every possible swap will has to be performed. The algorithm will repeatedly compare and swap nearly every element, resulting in a total number of comparisons equal to n times n-1 divided by 2. You can imagine this as the most inefficient state, where every record must gradually bubble through the entire list to its correct location. Finally, let's discuss stability. A sorting algorithm is stable if it's preserved the relative order of elements with equal sorting values. Bubble sort is indeed stable. For instance, if two students have identical scores, bubble sort maintains their original relative positions. Our implementations naturally adheres to this property as swaps only happen when one value is strictly greater or less than the other, leaving equal items untouched. In conclusion, Bubbles is intuitive and straightforward and stable, making it suitable for educational purposes or small datasets. However, its inefficiency in the worst case can be significant drawback. For a large dataset, more efficient like Quicksort or merge sort are generally preferable. Thank you.
Insertion sort. Insertion, insertion sort builds a sorted array one item at a time by inserting each new element into the correct position within the already sorted part. So insertion sort is a simple but effective sorting algorithm that's intuitive and commonly taught in computer science due to its straightforward logic. To illustrate clearly, I'll reference our FXML sorting insertion controller class, which demonstrates how insertion sort manages data within a Java FX table. So imagine you're sorting a deck of playing cards one by one as you pick them up from the table. Each time you pick a new card, you insert it into its correct position in your already sorted hand. That's exactly how insertion sort behaves. So here's precisely what happens in our Java FX controller. The program first collects data from a database into a list called max score list. Once the user selects the sorting criteria, for example, score, first name, or grade level, and decides whether the sorting should be ascending or descending, the sorting begins. The algorithm starts from the second element of our list in and considers the first element sorted array already sorted. From this point onward, each new element, we'll call it the key, is taken and compared to the element already sorted before. If necessary, those sorted elements are shifted to create the correct space for our new key element. In practical terms, suppose we are sorting by student scores from lowest to highest. The second student score is compared to the first. If it's smaller, the first student record shift one place, and our second student takes the first spot. This process continues with each subsequent student inserting each new record into its correct position, creating a sorted sequence incrementally until the entire list is sorted. Now let's discuss efficiently. Insertion sort is interesting because its performance varies significantly based on the original order of the data. In the best case scenario, when your data is already sorted, imagine a perfect list of students arranged neatly by ascending ID numbers. The algorithm is extremely efficient. It only needs to perform one simple comparison for each element. The number of comparison in this case is minimal, specifically only n minus 1 comparisons for a list of size n. Thus, insertion sort can quickly identify an already sorted array, giving it a best case times complexity of big O n. However, let's look at the worst case scenario, such as a list that is sorted in exactly the reverse order. Imagine needing to rearrange a set of student scores listed from highest to lowest into the lowest to highest order. Every new item you pick must be compared and moved all the way to the front of the list. This extensive shifting means the algorithm requires a significant number of operations. Specifically, for each element, it might perform as many comparisons as there are elements before it, leading to approximately n minus 1 times n divided by 2 comparisons overall, resulting in a worst case time complexity of big O n squared. And finally, one particularly valuable aspects of insertion sort, especially in practical software applications like ours, it is stability. Stability in sorting algorithms refers to the ability to preserve the relative order of equal elements. For example, if two students have exactly the same scores, a stable sorting algorithm ensures their original sequence remains unchanged after sorting. This can be crucial in many applications like our student record system. We're maintaining the integrity and order of identical data points matters greatly. Thankfully, insertion sort is stable, meaning it reliably preserves the original order of equal items, making it ideal for scenarios into multiple sorting criteria. In conclusion, while insertion sort isn't the fastest sorting algorithm for large data sets, its simplicity, stability, and excellent performance with nearly sorted lists makes it highly practical for many real-world applications, including the data management system we've discussed today. Thank you.
Next is selection sort. Imagine you have a list of numbers or names you want to sort. Selection sort works by repeatedly identifying the smallest or largest, depending on the desired sorting order of an element from the unsorted position of the list and swapping it with the first element of the unsorted part. Then, it moves to the next position, finds the next smallest or largest item, and repeats the process. By continually narrowing the unsorted section and extending the sorted section, the list gradually becomes ordered. Let's visualize this clearly with a short example. Initially, the list is 75, 85, 65, and 95. The algorithm searches the entire list for the smallest score, which is 65. It then swaps 65 with the first element, 75. Now our list would look like this after the first iteration. It continues with the process with 75, 85, and 95 because unlike the other sorting algorithm, selection sort is not purely optimized as it will self-swap its position by itself even though the list is already sorted on its own. So, unlike some algorithms like bubble sort or insertion sort, it doesn't significantly change its behavior depending on whether the data is already sorted or not. On the best case scenario, even if your data is perfectly sorted from the beginning, selection sort will still perform comparisons across the whole list each time. It always checks every remaining unsorted item to confirm which one is the smallest or largest. Therefore, even in its best scenario, it performs a high number of comparisons. In the worst case scenario, like the best case, when the data is entirely in reverse order, selection sort does exactly the same number of comparisons and similar swaps. Its performance remains consistently slow at approximately n times n minus 1 divided by 2 comparisons, maintaining a complexity of O n squared in a 1,000 elements or 1,000 entries in an array. The number of iterations a selection sort will do is 499,500. Lastly, let's address stability. Is selection sort stable? Unfortunately, selection sort is not stable. Why? Because the selection algorithm selects the minimum or maximum items and swaps it into place, even if the items are identical. If you have two students named Smith with the same score, their original order might unintentionally change during sorting. So, an example with this in the code would be this Luna and Aquino here because sometimes even if they have the same score, the original order sometimes unintentionally change during selection sort. To sum up, selection sort works by selecting and swapping the smallest or largest items repeatedly. It consistently performs a high number of comparisons, making it inefficient compared to algorithms like merge sort or quick sort for large datasets. And crucially, it does not guarantee stability.
So next is merge sort. Merge sort is a divide and conquer algorithm. It divides the array into halves recursively, sorts each half, and then merges the shorted halves. So imagine you have a large stack of exam papers, and your goal is to arrange them neatly by students, grades, names, or IDs. One intuitive approach would be to repeatedly split your stack into smaller, manageable piles until each pile contains just one exam paper. Then you start merging these tiny piles back together by piece into larger sorted stacks. This intuitive step-by-step approach exactly describes how merge sort works. And it's precisely what's happening behind the scenes in our JavaFX application through the FXML sorting merge controller. How merge sort operates in the controller. In our JavaFX controller, merge sort kicks into action whenever a user selects a sorting criterion such as ID, first name, grade level, or score and decides whether they prepare it sorted as ascendingly or descendingly. Let's break down this process clearly. Splitting first is splitting phase. Merge sort begins by checking if our list is already small enough to be considered sorted, specifically if the list has only one element. If not, it splits the list exactly into two halves. Each half then independently undergoes the same splitting process, recursively continuing until we're left with individual lists containing a single item. At this point, every tiny list is trivially sorted by definition. Then next is merging phase. Next comes the crucial merging step. We take this sorted single item list and start combining them into larger sorted lists step by step. Our JavaFX controller specifically merges based on the selected sorting field such as grades or names. Each merge involves carefully comparing elements from two smaller lists. For example, if sorting by score, it repeatedly picks the higher or lower score based on ascending or descending order and places it into a new combined list. These steps continue systematically creating progressively larger sorted lists until the entire collection is sorted and unified. Third is updating the UI. Once the sorting is completed, our application updates the visual presentation. The sorted list is set as the data source for the table view, reflecting the newly sorted state instantly. Additionally, the search filter is reapplied and to ensure the data on screen accurately matches any active search queries. Next is the base case versus worst case. Unlike many sorting algorithms, merge sort has the unique advantage of offering way predictable performance. Its runtime doesn't drastically change based on how sorted or unsorted your data initially is. Next is the best case scenario. Even if your data is already sorted perfectly, merge sort still performs its full splitting and merging process. It doesn't skip steps because it doesn't know if the data is already sorted. The good news here is that this predictable approach, which means you're guaranteed consistent performance no matter the original order of data. Next is the worst case scenario. Similarly, if the data is completely randomized or reversed, merge sort performs equally well. It still divides the list into tiny sorted pieces and merges them methodically. Thus, the worst case for merge sort is identical in complexity to the best case scenario, making it a highly reliable algorithm. In mathematical terms, both best and worst case complexities are represented as O(n) log n. This means that merge sort will always complete sorting tasks efficiently, even as the larger data grows substantially larger. Stability of merge sort. Another critical property of merge sort, and one that particularly valuable in database or UI context, is stability. A sorting algorithm is considered stable if it maintains the original relative order of equal elements. In practical terms, if two students have the exact same score, a stable sort ensures that they remain in their original input order. Merge sort achieves that this stability naturally. Our implementation explicitly maintains this stability through careful comparisons. If two items are equal during the merging phase, the item from the left side, which appeared first originally, is always selected first. This ensures that your original ordering isn't disrupted unnecessarily. Really, a crucial feature for consistent data presentation. Why merge sort? Merge sort is powerful because it is predictable, reliable, and stable. Its efficiency doesn't waver dramatically based on the initial state of your data, and its stable nature ensures data integrity remains intact after sorting. In our JavaFX based sorting controller or the FXML sorting merge controller, merge sort shines by offering users an intuitive, interactive experience. Whether you're sorting by names, grades, or other criteria, you can trust Mercer to quickly organize your data consistently every single time.
So next, I'll be discussing how heap sort works, particularly focusing on an example from a JavaFX application used to sort a table of student scores. We'll break down the process step by step, clarifying what happens in both best case and worst case scenarios, and explain why heap sort isn't stable. To start, heap sort is a popular sorting algorithm that organizes data by first building a special kind of binary tree known as a heap. A heap is a structure such that for every node in the tree, the value of the node is greater than or equal to the values of its children in a max heap, or less than or equal in a min heap. In our Java FX program, when we select ascending order, the algorithm builds a max heap to efficiently pull the large element and place it at the end, gradually sorting the entire dataset. So let's go deeper into how the process unfolds in our specific scenario. Initially, our dataset, which might consist of student IDs, first name, last name, grade levels, or scores, is stored in a table. When the user selects heap sort from the sorting options, the algorithm begins with the heapify phase. Heapify transforms the unsorted list into a properly organized heap. It starts from the last non-leaf node and moves upward to the root, repeatedly ensuring the heap property is maintained. This process ensures that the largest or smallest value based on the selected sorting order bubbles up to the top. After building the heap sort enters the extraction phase. Here, it repeatedly takes the top element, since we already know it's the largest or smallest, and moves it to the current sorted position at the end of the list. It then reduces the size of the heap one by one and heapifies again. This continues until the entire dataset is sorted. Each step ensures that progressively the data becomes more and more organized. Now, regarding performance, HipSort is remarkably consistent. In both best case and worst case scenarios, the time complexity remains the same, big O and log n. This consistent behavior makes HipSort very reliable, especially with large datasets. Unlike some algorithms like bubble sort, which have significantly different best and worst case complexities, HipSort guarantees predictability, even if the list is already sorted or completely randomized. HipSort always operates at the same efficiency, performing around 2n plus n log n comparisons. This calculation is reflected clearly in the labels provided by our JavaFX interface. However, one important aspect to understand about heap sort is its lack of stability. A stable sorting algorithm keeps equal elements in the original order, ensuring that if two students have exactly the same score, their relative positions from the original list remain the same after sorting. And unfortunately, heap sort does not have this property. Due to the nature of heap operations, the algorithm rearranges elements in a way that disregards their original positions. This means that after sorting, two identical scores might swap positions relatively to their original order. If maintaining the initial order of equal elements and is critical for your application, heap sort might not be the ideal choice. Heap sort might not be the ideal choice. In conclusion, heap sort is a powerful and reliable sorting algorithm, excellent for scenarios where predictability and efficiency matter, regardless of initial data arrangement. However, its instability means it isn't suitable for all contexts. Understanding the strengths and limitations helps developers choose the right sorting tool for their specific needs. Thank you.
Plus is the quicksort algorithm. Quicksort is a classic sorting algorithm that employs a divide and conquer strategy. Its main principle is to partition a large list into smaller sublists around a chosen pivot, recursively sort these sublists, and eventually combine them into a fully sorted list. It's particularly popular because of its efficiency in practical application. In our application, we sort max score objects, each containing several fields like ID, first name, middle name, last name, grade level, and score. The user selects the field to sort by. For instance, score and chooses either ascending or descending order. When the sorting begins, the quicksort algorithm selects the last element in the current sublist as a pivot, then rearranges the other elements so those smaller than the pivot are placed before it and those larger after it. Tabda yung pangitahanap ng sort. Yan ang quicksort. Then, let me break down the sorting step by step for clarity. First, we pick up pivot element in our implementation. This is consistently the last element of the current sublist. Next, we scan through the sublist, rearranging elements based on how they compare to the pivot. Elements less than the pivot move to its left, and those greater move to the right. Once this step is complete, the pivot occupies its correct position. The sublist is now divided into two smaller sublists around the pivot, and the quicksort algorithm recursively sorts these two partitions following the same procedure. An essential aspect of quicksort's performance is the choice of pivot, which directly impacts efficiency. In the best case scenario, quicksort achieves maximum efficiency by consistently selecting pivots that divides the list into two nearly equal parts. When this occurs, the sorting operation completes with a time complexity of big O of n log n. This logarithmic efficiency comes from repeatedly dividing the list into halves, significantly reducing the number of required comparisons and swaps. However, quicksort also has a notable weakness. Its worst case scenario occurs when the pivot continually ends up as either the smallest or largest element. In such cases, quicksort generally highly quicksort generates highly unbalanced partitions, essentially reducing the algorithm's efficiency to that of a simpler sorting algorithm, like selection or bubble sort, with a time complexity of big O of m squared. In our implementation, we show these cases numerically. The worst case iterations can approach in n times n minus 1 divided by 2, while the best case iterations approximate n log n. Lastly, let's address an important aspect called stability. Quicksort, by its fundamental operations, performs swaps based purely on comparison values and does not consider initial ordering. Therefore, it is not stable. After sorting, elements with identical sorting values might not preserve the order they were initially held. In summary, quicksort is powerful and efficient, especially when pivots are chosen wisely, but it carries the risk of degraded performance under certain conditions. While highly efficient in the average and best case scenarios with big O of n log n complexity, its worst case scenario can deteriorate to big O of n squared. Moreover, due to its internal swapping mechanism, quicksort does not preserve stability. Nonetheless, its practical speed and straightforward implementation continue to make it one of the most widely used sorting algorithms in computer science today. Thank you.
And that's all. Thank you.